Swayam Prabha. Digital India. Educated India.
In this class, we will discuss about certain concepts, principles required in studying a small system to predict properties of bulk materials. So now, if you look at typical MD simulations, you will see the number of particles. What I mean by particles is basically it could be atoms, molecules, or nanoparticles, colloids, surfactants, polymers, right? So typically we take 10 such particle or maybe 10,000 such particles. So that's a typical system size that is used in simulations. The reason why we use such a very small number of particles is because the system size is based on what storage that is available in our computing system, and also what is the speed with which we can do floating point operations in the computer. So based on these storage and the speed of operations, floating point operations, we are limited by a system size that is very small. And the main reason why this happens is that if you look at the MD simulations, so one of the major computing resource used is in calculating the potential energy, which goes as of the order of n square, where n is the number of particles, okay, because of the pairwise interactions. And of course, there are some special algorithms that can bring down the scaling from n square to order of n ln n, which we will see in the subsequent classes as a special algorithms. So, given that we have limitation on the system size that could be studied in computer, so if you ask what kind of physical system that we can simulate with such a very small number of particles, so if you consider a very small liquid droplet, maybe a picoliter or attoliter volume droplets, where the number of molecules itself is very small, or if you consider a very small nanocrystal or microcrystal which has about a few thousands of atoms, so then you can immediately study such very small systems. However, if you want to predict the behavior or measure properties of bulk systems, which are of the size of Avogadro number, which is 10 to the 23 molecules or particles, then doing simulation with such a large number of molecules is not possible with the current computing capabilities. So the main so then how do we study bulk systems? Turns out that we can still use very small system size and try to predict properties corresponding to bulk system, provided that we make certain measures to avoid the wall effects or surface effects. So one of the main problems that will come when we talk about very small system size is that the fraction of molecules on the surface is going to be far more significant, and the effect of walls of the simulation box will play a major role in controlling the property. Then in that case, we are not truly predicting a bulk system behavior, but we are rather predicting a behavior of a system confined by a simulation box walls. So how do we eliminate these surface effects? How do we use a very small system size but yet predict properties of a bulk system? So that is the context that we want to discuss today. Now, to give an example of what the surface effects means, or what I mean by a large fraction of particles would be on the surface compared to the total number of particles in the system. So let us make a very simple estimate. Imagine that you have a cube of simulation box, and of edge length, let's say L. Okay, so we are talking about a simulation box of edge length L. And let's say there are n number of particles. See, number of particles is n. Okay, so now let's fill this number of particles in a systems in a box of edge length L corresponding to certain volume fractions. Okay, there's going to be some volume fraction. Let us call this volume fraction as phi, and which is defined as number of particles times volume of one particle divided by total volume. Okay, so that is the definition for volume fraction. So here V1 is nothing but the volume of one single particle. Suppose if you think about a single particle having a diameter of sigma, spherical particle of size sigma, then V1 is nothing but pi by 6 sigma cube. Okay, so that is the spherical volume occupied by one single particles. So from here we will solve for n, which is 5 times V by V1, which is nothing but 5V. So what this expression tells you is that what is the number of molecules required to fill a box of volume V corresponding to a volume fraction of 5. Okay, and each molecule in this case has a size of sigma. So now we can also substitute for V, which is nothing but L cube. Okay, so this is the number of molecules required to fill a cube of edge length L with n number of particles with the size sigma and volume fraction of 5. So now imagine how many atoms are going to be on the surface of these cubes. Okay, there are 6 such surfaces. Okay, and then you ask how many such particles would be there on the edge or on the surfaces. So then that would be called Ns. Okay, Ns is the number of particles in the surface. And now let's also find out the area fraction, which I call 5s. That's basically surface fraction. That is equal to number of particles on the surface times area of one particle divided by the total area. So Ns is as such. So A1 can be written as pi by 4 sigma square. Okay, so that's a cross section area that I'm using. And then this capital A here is nothing but 6 times L square, because there are 6 faces of area L square. So 6 times L square. So you get when you simplify this, you get pi by 24 Ns sigma square by L square. So from here let's solve for number of particles on the surface Ns. So then you get 24 . So we got basically 2 expressions, one that is relating to the total number of particles in the entire system, and another expression for the total number of particles in the surface. So now let's find out what is the ratio of Ns by N. So this ratio will tell you for a given system size of L, sigma, and volume fractions and area fractions, what is the fraction of atoms on the surface versus the total number of atoms. So that's a fraction we want to estimate. So let's substitute for Ns and N here. So the fraction comes out to be 4 times 5s sigma by 5 times L. So now we have to choose certain values of 5s and 5. And if you have a closed packed circles on surfaces, so 5s is about 0.9 for a closed packed limit. And then the volume fraction phi in the cube can be as much as, let's say, 74%. So that's a typical numbers. And then suppose if you so now if you substitute all these things, you get 4.8 times sigma by L. So you can see that this fraction of surface atom inversely proportional to the box size that you want to choose, L. Suppose if you choose L as some 10 times sigma. Okay, so your box size is 10 times the particle size. Then you see that this fraction ns by n becomes about 48%. So that's roughly about 50% of the particles are on the surface. So that means if you take about 1000 particles for your simulations, of these 1000 particles, about 480 particles will be on the surface, and the local environment of the particles on the surface is very different from particles sitting in the interior of the bulk. So when you try to simulate a system with such a very small system size, and much of the properties coming from both the bulk particles as well as the surface particle, okay, then it will be very difficult for us to relate the property measure from simulation to an experiment, because in experiment typically we don't have surface effects or wall effects, because we are talking about a very large number of system size. So one of the way you can go about solving this problem is by increasing the value of L. For example, we could choose L to be something like 100 times sigma, right? So then this ns by n becomes about 4.8%. Okay, that means if I take 1000, if I take a certain number of particles and having a box size of 100 times sigma, then you basically have roughly about 5% of the particle on the surface, which is reasonable, and because 95% of the properties are coming from the bulk atoms or bulk particles. But however, the catch is that to have a box size of such a large size, 100 times sigma, for the same volume fraction, your number of particles will have to scale 3 orders of magnitude larger. Okay, so here we said if n was something like 10 power 3000, so here this should be about 10 power 6. That's the range we are talking about. So now we already said that the computing power goes as n squared. So when you go from system size of 1000 to 1 million, and then the amount of computational power required to solve such a big system also goes up by order of magnitudes. So that's the problem of choosing a system size. On one hand, we want to have a reasonable system size so that it can be it could be solved in a computer. On the other hand, the system size should be sufficiently big enough so that we can avoid the surface effects and wall effects. So that's something. So whenever you set up a simulation, this is the first question that you ask: what should be my system size? Whether there's going to be any surface effect or not? How realistic is it? Okay, these are some of the questions that you want to answer. So with this rough estimate of the surface effect, and recognizing the fact that you cannot just simply go with a small system size and then anticipate that you can predict a bulk property. Okay, so we have to do something about it. And there are methods by which we can actually handle this problem. We can still use very small system size, yet eliminate all the surface effects, so that we can be confident that we are able to predict bulk properties. So in order to do this, to eliminate the surface effects, we use what is called periodic boundary conditions. So this periodic boundary condition is not a very new concept. So if you have solved any PDE or ODE, you would have already used this kind of a periodic boundary conditions when you do discretization of space. So here the idea is same, but implemented slightly differently. So in this case, what we are trying to do is try to use periodic boundary conditions to eliminate surface effect, so that we can mimic the bulk-like behavior in the simulation box. So the way we do that is, we take the simulation box. So in this figure, I am showing a 2-dimensional representation of a simulation box. So the central square that you see here, so that is our simulation box. Okay, it's a square box. In 3D, this would be a cube. We will discuss everything with respect to 2D, and then we expect a similar argument holds for 3D as well. So in the simulation box, we have a certain number of particles which are indexed 1, 2, 3, 4, 5, etc. Okay, so these are not shown as spherical but elliptical, just for generalization that we are talking about molecules and not necessarily spherical particles. So now what we are going to do is, in the periodic boundary conditions, what we are going to do is you take this central simulation box and then you replicate the same box in the entire space. Okay, so we replicate the simulation box throughout the space to form an infinite lattice. So what we have shown here is the nearest neighboring boxes, but there are basically boxes everywhere around it, but they are exactly identical. you can see that the same molecule 1 here is represented here in this box, image box A. Similarly, if you go to this periodic image B, again the same molecule 1 is sitting here. If you go to the periodic image C, box C, again the first molecule is here, and so on, so D and E and everything. And you can see that each of these periodic images have the same dimension, edge length of L, just like the central box. So now the way the reason why we do this is because if you think about atoms and particles moving in the central box, simulation box, and then if you think about what's happening in its images, exactly same process happens in all the images also. For instance, if this molecule 1 were to cross this boundary and go here, and you might think that in the central box one molecule is lost. However, if you look at the image G, you can see that the periodic image of this molecule 1 from this box is coming into this point. So that means when a molecule moves across a boundary, it actually enters from another periodic image to the central simulation box. In a way, the number of particles in the simulation box is always conserved. So we never lose any particles during this process. In other words, this molecule, when it crosses a boundary, it doesn't really feel any boundary. There is no any effect of this boundary here, because anytime something goes out, it's basically coming from the other side, like a loop. So that's what is mentioned here. If a molecule moves out of the simulation box, one of its periodic image or the same molecule from one of the periodic image enter from the opposite side. That's what I was trying to explain here. If this molecule goes to box C, the same molecule from box G would enter from the other side. Okay, so thereby we keep the number of atoms in the central simulation box conserved, and also we eliminate by this way the effect of the boundary, because the molecules does not really feel any repulsion or any sort of interaction when it crosses the boundary. And one of the important thing is that when you think about this central simulation box in all its periodic images, we don't have to necessarily bookkeep the coordinates of all the molecules in the periodic images. We just have to store only the position in the central box, because the moment I know the coordinates of the periodic images, and I can easily relate what is the position of the periodic images of particles in all the other boxes. So we have to only remember or bookkeep the coordinates, positions and velocities of particles only in the central simulation box. We don't have to bookkeep for the neighboring images, because these are all periodic images anyway. So this is a very important concept. It is used pretty much in every MD simulations trying to predict any bulk properties. Now the question is, to what extent this periodic boundary condition, which we have introduced to eliminate surface effects or wall presence, will this affect the bulk properties? So that's a very important question to ask, and the answer to this question depend on two things. One is, what is the range of the intermolecular potential that we are using, and what is the physical phenomena that we want to predict? Okay, it depends on two such factors. Now coming to this intermolecular potential, if you consider Lennard-Jones, which scales as 1 by r power 6, okay, which is considered to be a short range, then you could actually do a simulation with a very small box size, something like L equal to 6 times sigma. It is possible to do a simulation with such a small box, yet you don't have any, without the particle being able to sense the symmetry of the periodic lattice. So what I mean by that is, when you have a very short ranged potential, when the potential quickly falls, then you can have a sufficiently small simulation system size, and yet each of these particles do not really feel their images sitting in the neighboring boxes. Okay, so that periodicity of the lattices do not impose any structural effect on the properties of the fluid that we are predicting. On the other hand, if you look at long range forces like Coulombic or dipolar interactions, which goes as 1 by r or 1 by r power 3, which are long ranged, then it basically essentially means that you have to have very large simulation box. Then the system size will go up, then the computing time also required will be very high. So then it's not feasible to do such a long range potentials. But we will talk about certain special techniques to handle such long range interactions. So what I'm trying to say is that as long as the potential quickly falls like an Lennard-Jones, we will expect that the periodic image or the periodic boundary condition will not influence the structural and dynamical properties of the system. Okay. However, this is not true for long range. So we have to account for the long range potential with some certain special techniques known as evolved summation and other types, which we will cover it in later lectures. So this is about potential. The other effect is about what is the physical phenomena that we want to study. As long as you look at behavior of homogeneous and single phase fluids, the density fluctuations are very small, and you can do simulation with it. But then when you try to simulate any system very close to phase transition, then you will see that the density fluctuations are macroscopic, and the box size L will basically limit what is the wavelength of this fluctuation that can be accommodated. So now the problem here would be the simulation box will restrict any wavelength of size L and above. Okay, so the maximum length scale of the fluctuation can be only L, but not beyond. But in real system, the fluctuations are macroscopic, which goes beyond L. So what that will mean is your simulation will not allow a large length scale fluctuations. That means your system will not phase separate. It will not truly predict the actual physics of the problem. So we have to be extremely careful when we apply simulations when we are very close to phase transitions, because fluctuations are macroscopic and simulation will not capture such a large length scale fluctuations. So then the consequence of this would be the phase transition that you study with simulation will be of different order. So what I mean by that is, suppose if you predict the heat capacity versus temperature. Okay, if you're predicting a if you're studying a first order phase transition, you expect a divergence of C of V about transition temperature T. Okay, so if you do experiment, you will see this kind of a divergence of C heat capacity at transition temperature. But when you do simulation of the same system with the fact that there is a phase transition happening, what you might actually see is not this kind of a divergence, but you will see something like a continuous change. Okay, so when you have this kind of a very smooth C of V, then we might identify this as a second order phase transition, whereas the true phase transition was a first order phase transition. So we may be incorrectly saying the order of transition studied in simulation to be of different kind than what is actually. So these are some of the subtle points that we have to keep in mind when studying phase transitions with MD simulations. Okay, so these are the two important things that we have to remember whenever we apply periodic boundary conditions. We have to worry about what is the range of potential, whether it's short range or long range, and the other thing is whether we are looking at any large length scale fluctuations in the system. It can be density fluctuation or other type, and then whether we are very close to phase transition or in a single phase or mixed states. Okay, so these are very, very important. So despite these warnings, in most of the cases, PBC has very little effect on predicting the equilibrium and structural properties as far as you are away from phase transitions, and such things work for short range interactions. So in any cases, one of the easiest thing you can do about whether periodic boundary condition is influencing your results or not, the best thing you can do is you basically just double the system size and then try to find the properties, and then you compare whether increasing the box size has affected my results or not. Okay, so that's the easiest trick you can do to verify any sort of influence of periodic boundary conditions on the properties that you measure. So now in the periodic boundary condition, I showed a square box in 2D, and then in 3D this will be a cubic box. And most of the times we take a cubic simulation box because as you will see in the subsequent slides, that coding the periodic boundary conditions becomes very easy. But that doesn't mean that we are limited with only cubical shape of simulation box. There are certain other simulation box shapes that are sometimes used. One is known as this truncated octahedra, and another one is rhombic dodecahedra. Okay, so this truncated octahedron is shown here, bounded by a cubic box, and then here also rhombic dodecahedron is shown within a cubic box. And as you can see, if you look at the shape of these non-cubical boxes, they look very isotropic, close to spherical geometry. So if you want to study isotropic fluids, people have found that there is little advantage of using non-cubical simulation boxes. But however, when you try to see the computer code for implementing periodic boundary conditions and force calculations, it becomes a little bit tricky to do coding. Okay, so so you have to look at what is the advantage of using the non-cubical box versus how much computing complexity that you want to involve. But for most of the practical purposes, you will see, if you look at research paper doing MD simulations, they often go with cubic box. But I want to just inform you that we are not just limited by only cubical box. Any space filling geometrical shape should work, such as truncated octahedron and rhombic dodecahedron. This is something for us to keep in mind. Now, if you remember, we were talking about this potential energy for the system, which comprises of the pair interactions. We looked at various forms of pair interactions, but there was also this unibody interactions, which mainly comes from external field. If you're talking about any electric field or gravitational field or any external field, then the potential depends on the position or the coordinate of the particles. Now we have to think about using this kind of external field in addition with the periodic boundary conditions. Now the fact that when you talked about periodic boundary condition, we said the simulation box is replicated in space as a periodic lattice. So then the form of the potential V1 should also have a same periodicity as that of the simulation, the periodic images itself. If this is not possible, then we have to worry about how to do such simulations. So as far as the external potential is periodic, just like way the simulation boxes are periodic, then there's no problem. In other cases, the periodic boundary condition has to be either dropped or some special techniques have to be used. To give an example, adsorption of methane on graphite was actually done on a substrate, and the substrate has a shape of a rhombus. So again, it is shown in here. This is the surface, which basically is a rhombic shape, and then normal to this direction, the z direction, we don't have any periodic conditions. So in this x direction and y direction, there is a periodicity, and the shape is not square, but it is a rhombic. And the z direction, on the bottommost surface is actually a surface. It's actually impermeable surface. So that means the molecule cannot go through them. So either they can adsorb or they can desorb. Okay, they cannot go through them. So this basically is like a physical substrate, physical wall. And this shape was chosen because it actually mimics the shape of a graphite material. Now, even though periodic boundary condition is applied on x and y direction, that means if the molecule is actually leaving to the left, it will enter to the right, and if they go from the top, it will come to the, if it goes from here, it will come back through the other side. But then if you look at the normal to this particular plane, so that's a z direction. So there PBC was not applied. So then the question is, what will happen if the molecule keep drifting away in the normal direction? So in this particular simulation, what they did is that beyond certain distance of Lz, okay, when the molecule tries to go away from this Lz, the molecule's velocity was actually reversed. So when the atom was trying to move away, the velocity is switched so that it comes back down. Okay, so this is an artificially induced wall effect, right? Because it's not happening in reality. In reality, in experiment, it would be just a simple substrate exposed to a gas of methane, and then you can adsorb and you can desorb and you can diffuse away. But here, when you try to mimic or when you try to simulate such a system, you are basically artificially inducing a wall effect on the top, so as to make sure that the atoms are always conserved, the molecules are always conserved, and you are not losing any of them moving away. So now the logic that why this method works is because if you keep sufficiently large length, edge length on the normal direction, this kind of a reflecting boundary condition will not really affect the results. The way you can confirm this is you take a simulation with a certain particular Lz value and then predict some properties of adsorption, and then you double the size of this Lz, and then you see whether there is any dependence, and you keep increasing until you reach a threshold L value, that is a normal edge length, and then you see up to when you can trust your data that is not dependent on the LZ value on the top. So these are some of the ways in which you can handle this kind of physical situation of such like adsorption or external field. So now we'll again talk about the periodic boundary condition and how it is implemented. So generally, if you look at the calculation of interaction energies, we often do this pairwise interactions. That means counting all the pairs, the distance between those pairs, using that pair distance in the potential function like Leonard-Jones or other kinds. So in general, if you consider this molecule 1, we are basically interested in calculating the interaction energy between molecule 1, 2, 1, 3, 1, 4, 1, 5 within the simulation box, but also all the other images in the neighboring periodic boxes also. However, to speed up the computation and minimize the computing time, an approximation is made which basically says that instead of looking at interaction with all the images, okay, we will just take only the closest image of a molecule, so that we will have the maximum contribution in energy, because most of the times the interaction energy quickly falls. Like Leonard-Jones, it goes as 1 by r power 6. So the most important contribution will come from the closest image than an image sitting far away from each other. So in that context, suppose if you want to calculate the interaction energy between molecule 1, you will see that between 1 and 2 is happening within the same box. But if you look at 1 and 3, you have this. At the same time, you also have the other image coming from here. So if you look at the distance wise, this distance is actually much smaller than this distance. So instead of calculating the interaction energy between 1 and 3, you will calculate the interaction energy between 1 and the molecule 3 in box E. So that's what I call this 3E. So 3E basically means the third molecule sitting in the periodic box E. Similarly, if you look at 4, the distance 1 to 4 within the same box is little larger than the image 4 sitting in box E. So this distance is smaller. So we consider the interaction between this molecule 1 and the periodic image of molecule 4 sitting in the box E, that is 1 to 4E. And then if you look at the fifth molecule, then again the distance between 1 to 5 is this, but there is a periodic image in C which is closer. Okay, of course there is a periodic image of 5 here, 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 and so on. So, but among all these images, the closest image is this, and this is closer than the same molecule sitting in the same box also. Okay, so now instead of taking this distance, we take this distance. The logic behind doing minimum image distance is the fact that the image which is closest to the molecule has more contribution or maximum contribution to the interaction energy than something sitting far away from each other. So in effectively what we are trying to do is, whenever we find interaction energy, we take that particular molecule and then you sum over all the other molecules within the same simulation box, but also with the other images, and then for any pair you ask whether I should take the closest, you basically find which is the pair that is having a shortest distance of separation, and you take that. Okay, so in this example we see that the molecule 1 and 2 in the same simulation box are the smallest distance, so we take that, whereas for 3, 4 we take from image in box E, and for a fifth molecule we take the image from C. So this concept is called minimum image convention. So this is an approximation made so as to minimize the number of computing iterations, at the same time having a maximum contribution to the energy. So in this method also we have not made any reduction or any change in the number of pairs we have to sum over. In this particular example also, for every molecule you are going to sum over all the pairs in the system. So effectively you are talking about half into n minus 1 number of pair search in this particular system. So this is basically roughly scales as n square, like I said before. Okay, so in simulations, when you calculate the interaction energy, you basically look at the closest image and find the distance between those images, and then use that distance for the calculation of interaction energy. So that is called minimum image convention. This is very important concept that is used in all simulations. Now, I did not talk about the circle in the previous slide. Now we can make another additional approximation. You can improve the computing process a little better by defining what is called a potential cutoff. So if you remember Lennard-Jones potential, it goes something like this, right? So this is basically this is R, this is ULJ. Okay, this is a minimum, and this is sigma. So now what is generally done is, instead of looking at all the pair interactions, you consider only pair which are up to certain distance r cut. Okay, we define a variable called r cut, a parameter called r cut, and we basically truncate the potential at this point, and then we see that beyond any pair beyond this distance, we keep them as 0, interaction energy 0. The advantage of doing this potential cutoff is that I have to now worry about only pairs which are within a distance of up to r cut only. I don't have to consider any pair which falls beyond r cut value. This greatly improves our number of operations that we need to do in calculating potential energy. So let's see how we can implement this potential truncations. So we are looking at the central simulation box, and then its periodic images A, B, C, D, E, F, G, H. These are all periodic images. And then with respect to molecule 1, like we said before, the minimum image convention will tell you which are all the images that we should be considering. Okay. So in the previous case, we looked at all combinations 1, 2, 1, 3, 1, 4, 1, 5. We took all of them. Only difference in minimum image conversion was whether to take the molecule from the same simulation box or from the closest images. That's the only approximation we made. But now with the potential truncation, what we can do is we can define a distance from each molecule up to certain radius RC, that is a potential cutoff, and look at or focus only atoms and molecules within that particular sphere or circle, and don't consider any pair falling outside the R cut. So by that, you will see, once you have that potential cutoff, now you can see that the interaction between 1 and 2 should be considered, because the pair distance 1 and 2 is within the R cutoff. Similarly, if you look at 1 and 3, I already said that we are not taking this, but we are taking the periodic image here, but this distance is falling beyond RC, so this will not also be counted because of the potential truncation. And if you look at molecule 4, we said its periodic image in the box E was considered, and you can see that this is actually falling within the potential cutoffs, so we are going to take this interaction. So the and then typically if you look at molecule 5, its periodic image 5 was considered here, but the center of molecule 5 here is away from RC, so we are not going to consider this also. So effectively, the meaningful contribution comes only between 1 and 2 and 1, 4E after applying the potential truncation. So now how much are we able to save the number of computing operations? So that depends on the ratio of the volumes of the sphere versus the cube. Suppose if you did not have this cutoff, you would have considered all the pairs in this entire cube. Okay, so the volume of that is L cube, whereas now with the potential cutoff, you are effectively looking at a spatial region enclosed by this sphere of radius RC. So that is going to be 4 pi 3 RC cube. So this is a ratio, this is the factor that tells you how much computing, saving is possible with the potential truncation. Now, when I said about cutting the potential at a particular distance and where to cut it becomes an important question. As far as Lennard-Jones potentials are concerned, it is usually cut at 2.5 sigma or sometimes even 3 sigma. So when you look at 2.5 sigma, at this point, the potential energy will be very, very small. Okay, so we calculate the potential energy corresponding to R cutoff. So that is going to be about 0.16 sigma. Actually, this is a minus sign here. Okay, the potential energy here is minus 0.16 epsilon. So you are basically truncating the potential from this point, and then after that you are neglecting. So this cutting the potential or truncating the potential and then using simulation of this kind will alter the properties a little bit, and then we need to apply what is called long range corrections. So this long range correction, how to do, all that we will discuss in the coming classes after we discuss about statistical mechanics. And here is an example which showed the effect of having cutoff and correcting for it. What is shown here is temperature versus density for Lennard Jones. And so suppose if you just want to truncate the potential like this, then you will predict the critical point around here. Okay, this is basically a vapor liquid equilibrium. So on the left hand side you have a gas, on the right hand side you have a liquid. So this is a liquid phase and this is a gas phase. And suppose if you actually, after correcting for the tail correction, you see this critical point moves up to the, this is the correct value after correcting for long range corrections. So what I'm trying to say is that, when you look at MD simulations, we make a lot of approximations so that it is feasible to eliminate a lot of these effects, surface effects, and try to improve the computing speed by eliminating unnecessary interactions, and then also at the same time correcting for it after the simulation is done. So those are the points that we need to keep in mind. Another important thing we have to remember is, when you think about R cutoff, of course you have to see how much energy that you are neglecting. In this case we saw that by choosing 2.5 sigma for Lennard Jones, we are basically ignoring energy of the order of minus 0.16 epsilon. And then if you go to 3 sigma, you will see that this will come down even smaller. Okay, so that is one guiding principle for us to decide what should be the cutoff. Now another important thing we have to remember is that the cutoff should not be greater than half of the box size. This is because we are also applying the minimum image convention to find the nearest neighbors, and the potential cutoff and the minimum image convention goes hand in hand, so that this condition should be always maintained. So these are some of the important aspects that you need to keep in mind. So now the question is, how do we implement minimum image conventions and periodic boundary conditions in a computer code? So that's very easy to do. If you think about a simulation box centered at origin, and so that you can see the edge lengths are plus or minus L halves, and suppose if a molecule is actually moving from, crossing this boundary, and then the same image from the periodic image on the left will try to enter here. Okay, we want to basically do this in a computer code. The way you do that is, you check at any given point of time, you check whether your X position is greater than half of box length. So that means if this molecule goes here, this condition will be satisfied. Okay, so when this molecules escape this box, then its position is above L half in X direction. So in that case, you basically change the particle coordinates by subtracting a box length. Box L here is basically box length L. When you subtract the box length from its coordinate position, what that means is, this particle will be put back here. Okay, so that is what being done by this particular statement. It is also possible that the particle actually move to the left at any point of time. So suppose if this molecule actually comes here, so that means it is actually crossing the left side boundary, then the periodic image on the right hand side will push the particle at this point. Okay, to check this condition, you check whether the particle position here at this point is less than minus L half. So the boundary here is L half minus L by 2, and it is actually less than minus L by 2. So if that is the case, you add to the coordinate of the particle, you add the box length L. So when you add L, the box length, to the X coordinate of this particle, this will basically translate to this. This is a simple translation of moving the particle by a length of box length. So you can see whether in this operation or in this operation, whenever the particle crosses the boundary, another particle from the image comes back, so that the number of particles in the simulation is conserved. So we check whether the movement is to the left to the right or right to the left for all the coordinates, just like how we have done for Rx. Similar thing has to be done for Ry and Rz also. Okay, so at any point of time, you have to, whenever you make the particle move, at that time you have to see whether the particle has escaped the box boundary. If so, you put it back from the other side by simply translating the coordinates by an amount of box length, by adding or subtracting, depending upon whether it moves to the right or to the left. So this is the way you would do this periodic boundary condition implementation. And coming to this computer code for minimum image convention, in this case, what we do is, you may recall this pseudocode on the left, which is basically we discussed for calculating interaction energy for Lennard-Jones. And right after you calculate the distance between I and J, right after this, before you go to calculating the distance and potential energy, at this point you again check whether this Rxij is greater than box 2 or not. If so, you subtract the box length. Similarly, if Rxij is less than minus box 2, then you add the box length. By doing this operation, we can choose the image which is closest to the target molecule. So after you do this for Rxij, similarly you do for Ryij and Rzij also. So remember, in the periodic boundary conditions, we look at particle coordinates Rxi and Ryi and Rzi, whereas in the case of minimum image conversion, we are looking at the separation between I and J. So that's why we have looked at here Rxij, and then compare whether that distance is above or below the box half of box length, and then depending upon that, you add or subtract the box length so that you can get the minimum image or the closest image to the target molecule. After conditioning the Rxij by this operation, then you go about calculating the distance and then using it to calculate the potential energy. So this is how you do minimum image conversions. So as you can see, what we are trying to do is, first we showed how to calculate interaction energy in a double loop conditions. So now we are trying to say how to implement periodic boundary conditions and how to do minimum image conversion within that calculation of energy loop. And the final point is how to implement the potential cutoff. So in potential cutoff, what we need to do is, right after you calculate the Rij square, so this is basically Rij squared. So at this point, you check whether this distance is less than Rc squared. Now you may ask, why am I checking whether this is Rij square is less than Rc square instead of checking Rij is less than Rc? So the reason is that if you want to do this, then you have to take square root of these functions, okay? And taking square root is a little expensive. So instead of comparing this, you compare the square of these functions. Okay, so now only if this condition is satisfied, then you go about calculating these Ij interactions via Lennard-Jones. If this condition is failed, you don't do it. Okay, so you can skip set of operations. You can actually skip this set of operations because these are not going to add any energy, because the energy here is 0 beyond potential cutoff. So at this step, we had to do the minimum image conversion. After that, you calculate the Rij square and then check whether Rij square is less than the R cut square or not. Only if then you calculate Ij interactions. Otherwise, you go to the next pair and keep searching for the important pairs. So this is one way. The other way to do would be instead of coming all the way here, you can also check whether this R cut is comparable or not. Even in the right after you implement the minimum image conversion, you can check individually whether Rxij is less than R cut or not, and similarly Ryj is less than R cut or not, and so on so. And then you calculate Rij square and then you go to this. This is another way of doing it, but either of them is fine. It's just that in this case, you are basically looking at multiple if statements. But the advantage of doing this is that even if one of them is actually satisfied, you will skip the loop, you will go to the next pair. Whereas in the previous case, you may have to calculate Rij, Ryij, Rzij, and then you calculate whether the potential cutoff is meaningful or not. But in this case, we can actually capture this violation of this condition within one of these 3 if loops itself. But then again, multiple if loop also accounts for more computing times. So there should be a balance between how much time we save by doing this individual checks versus the overall check. So what I'd like to summarize about this lecture is that so the important point to remember is the simulations are always carried out with a very small number of molecules compared to a experimental system size. Okay, so that is because of limitation of computing power. And we can eliminate these surface effects or boundary effects by properly implementing periodic boundary conditions, so that even though the simulation has a very small system size, you can still try to compute bulk properties. And we also talked about different kind of box shapes and about minimum image convention, so as to incorporate the most significant pair interactions and then potential truncation to speed up potential energy calculations. Thereby you can eliminate redundant pair calculations. And then also we looked at the computer pseudocode for implementing periodic boundary conditions, minimum image conventions, and also potential cutoffs. So if you were to write your own MD code, these are all the steps that you have to keep in mind. If you are using a software or open source software, but you have to remember that these are the things that are implemented in those open source codes as well.